In this video, we're going to look at trees. A tree combines the best features of an ordered array and a linked list. Like an ordered array, it allows for quick searching, and like a linked list, it allows for fast insertion and deletion. And so here we see an arrangement of nodes, which are the blue circles, and these represent objects. And these nodes are connected together by edges, which represent the relationships between the nodes. And this tree-like diagram can be modelled using a linked list. If you remember, the nodes of a linked list contain pointers to the next node in the sequence. And whilst we're not going to be following a linear chain this time, we are still going to be having pointers to the next node in the tree diagram. It's just that the nodes will have multiple pointers this time, rather than one. But before we get into the implementation of the tree data structure, let's get accustomed with the particular terms that we're going to be using. And so to get to a particular node in the tree data structure, we have to follow a path. As you can see here, if we wanted to get to node J, we have to follow first through A, C, and F to get to J. Next, we should know that the root of the tree is the node at the top of the tree, which is A in this case. Unlike physical trees, which grow outside and have an entire root network, the tree data structure only has one root node. And the tree data structure also refers to nodes as either being parents or children. We can see here that the node C is the parent of nodes F and G. And likewise, nodes F and G are children of the node C. In the exercises that correspond to this video, we're going to be implementing a binary search tree, which is a particular type of tree data structure. And in a binary search tree, it's worth remembering that each parent is only allowed to have a maximum of 2 children. Next, the term leaf describes nodes that are at the bottom of the tree data structure, which have no children. So here you can see that nodes G, J, I, E, and H are considered to be leaf nodes. And then we also describe the nodes of the tree in terms of levels, with level 0 being the top of the tree, the root node, and then the levels increase as we go further down the tree. We should also make a distinction between the terms of visiting and traversing. When we want to visit a particular node in a tree, we have to follow a path, as we said earlier. However, passing over a node en route to another node is not considered to be visiting those nodes. So in this path, we would only visit node J. We wouldn't visit nodes A, C, and F, because we merely pass through them en route to visit node J. However, when we traverse the tree, we do visit all of the nodes in the specified order. So, whilst there are many different ways of arranging nodes within a tree data structure, we're going to be focusing on the binary search tree, or BST for short. And as the name implies, the nodes within a binary search tree are arranged so that we can perform the binary search algorithm. And if you think back to when we implemented the binary search algorithm with an array, we had to consider whether the item that we were searching for was greater or less than the middle value of that array. And then we would disregard the other half of the array and repeat the process. So this is the same principle that we're applying here with the binary search tree. So in order to be able to search in logarithmic time, O of log n, we need to ensure that the binary search tree only has a maximum of 2 children for every parent, called the left child and the right child. And it's also important that the left child has a value that's less than the value of the parent and also less than the value of the right child. So that when we want to search for a value which is less than the value of the parent, we know to choose the left-hand side of the tree. And when we want to search for a value that's greater than the value of the parent, we search through the right-hand side of the tree. So when we have a look at the design of the classes, we see that we've got a node class, which is similar to the node class of the linked list, but rather than having a single pointer to the next node in the linked list, we've got pointers to the left child and the right child this time. And rather than having an integer data value, we've actually got an object of another class called data, which is basically just a wrapper class for multiple variables, where we've got an integer variable for the ID and we've got a string variable for data in the data class, which is up above. Okay, so that's the node class. And then we've got the management class called binary tree, which contains a pointer to the root node, the first node in the tree, and then has methods for the operations, such as find, insert, and delete. Okay, so for our first exercise then, let's have a go at implementing this design to get started with creating a tree data structure. Let's get this tree set up then. So in exercise 1, we're given the node class code. So let's set up a class for that in our project. And so we're given the header and the CPP file, but just to keep things all on one screen, make it easier for us to follow, I'm going to just set up a header file. But of course, please do go ahead and create separate files if you would prefer to do so. So let's set this up then. We're given the public interface, and this also contains the attributes. So this has the left child and right child pointers. And so at the minute, we're modeling data as just an integer variable. That may well change later on throughout the exercises. And then we've got the constructor, the node constructor, which assuming nothing's changed, that's just going to assign the data, yes, to the class variable data, yeah, and then we've got a display method which just prints it to screen. Okay, so I'm going to need to include namespace, std, and iostream if we're going to be printing stuff to screen. Okay, so let's just copy this code in. Oh, and also in the node constructor, we're also going to be initializing left child and right child to 0. So they'll just be empty pointers until they're assigned to when we get to the insert method. That's coming up later. And then for the display method, just going to copy that line of code in, which just prints out the data to the screen. Okay, so that's the node class. That's exercise 1. Let's scroll down and have a look at exercise 2, which is to create the tree class. So let's go ahead and add that here. I'm going to do the same thing again. So I'm just going to create a header file for the tree. But again, you know, if you want to create 2 files, header and CPP, that's absolutely fine. There we go. And I'm going to copy in that public interface again, which of course contains a mixture of attributes and methods. So it's looking for a reference to node, so I need to include that. Include the node class there to get access to it. And so we can have an attribute which represents the root of the tree, the first node in the tree. As we said before, that's going to be the first one that's inserted into the tree. And next we've got the methods. We've got the constructor, which just initializes roots to 0, that pointer. Okay, when we first instantiate the tree. And next we've got find. Okay, so this is the search method, which we're going to be talking about in the next video, which is the next slides that we're due to jump back into after this. So I'll explain more about how that works then. And also, we've also been given the in-order traversal, which again is another method I talk about in the next slides. Okay, so I won't say too much about that now, but we'll obviously talk more about that in a few minutes. Okay, so this is all we need for now for the tree class. As I say, let's jump back into the slides then, where I'm going to talk through the thinking behind these particular methods, the insert method, the find method, or searching through the tree, and also traversing through it in the display in order method. Okay, so let's jump back into the slides. Right, so now that we've set up the tree and node class, let's take a look at inserting nodes into the tree. And so the first node that we insert in the sequence automatically becomes the root node. And since we're using a binary search tree and not an AVL tree, which self-balances itself, it would be wise to choose a value which sits roughly in the middle of the range of values in that data set to try and create a balanced tree where there is roughly the same amount of values on the left-hand side and the right-hand side. And then the next values, the next nodes to be added, would then be compared against that root node. So here in this example, the first node that we insert is 63, that becomes the root, and then the next node to be inserted is 80. And as 80 is greater than 63, that's going to be inserted on the right-hand side of the root. That's going to become the right-hand child of that root node. And then after 80, the next value to insert is 70. And as 70 is greater than the root node, 63, the first level, we then go down to the right-hand side of the root and then compare 70 against 80. And as 70 is less than 80, 70 is then placed as the left-hand child of 80. Okay, so hopefully you're seeing the process here of how we insert items into the tree. And this process of comparing the new item's value against the items already in the list to work out whether the new item's value is greater than or less than the values in the list, we can model this algorithm recursively. So if you remember back to the video on recursion, you'll remember that the recursive method is a method that calls itself. And here, in the pseudocode for the insert method, you can see that there are calls to the insert method again for the less than and greater than comparisons. And the process of searching the binary tree is very similar to that of the insert method. We start by comparing the value or the key that we're looking for with that of the root node to work out whether the value that we're searching for is in the left-hand side of the tree or the right-hand side of the tree. So here, if we're searching for the value of 57, we first compare 57 with 63, of which 57 is less than 63. So we then go to the left-hand child of that root node and then compare 57 with 27. And as 57 is greater than 27, we look at the right-hand child of that node and then repeat those comparisons until we find that value of 57 in the tree. And as we're repeating the same process for each level of the tree, we can also model this using recursion. You'll notice that if the item, I in this case, is less than the current node that we're looking at, which is root in this case, then we return a call to search passing the left child of that current item that we're looking at to the search method again, and then repeat the process until we find a matching key. When it comes to traversing the binary tree, and remember that traversing means that we visit all the nodes in the tree, there are several different ways that we can print the items in the tree. The particular method that we're going to be using in the exercises is in-order traversal, which means that we print out the values in ascending order, basically, meaning that we'll always start with the left-hand child, which is the smallest of the values, and then we'll go to the root, and then we'll print the right-hand child, so that we then print out the items in ascending order from lowest to highest. And as you can see, we're writing this method as a recursive method, because of course we're repeating the same process for every node of the tree. And lastly, let's have a look at the process for deleting a node from the tree. And this time, the algorithm for this will depend on how many children that the particular node we want to delete has. So if the node that we want to delete is a leaf, meaning that it has no children, we can set the parent's pointer to this node that we want to delete to be null. So you can see here, if we want to delete the value of 82, we just have to set the parent, which is 92, we have to set its left child pointer to null. So this is easy enough, but when we look at deleting a node which has one child, we have to change the approach slightly. And this is because we want to make sure that the child of the node that we want to delete is placed in the right position to maintain the binary search functionality. And in this case, because the child node having the value of 82 is still greater than the parent of the node that we want to delete, which is that parent node is 80, because 82 is greater than 80, we can effectively replace the node that we want to delete with the child node, which is 82. And if we want to delete a node which has two children, we'd have to identify the node which has the next largest key value. So in this example, because we want to delete the node 80, we'd have to consider the right-hand side of that node, which has values 92 and 82. And because 82 is the next largest, we then replace 80 with 82, as this will allow us to retain 70 and 92 in their original position. We don't have to worry about moving those two, or indeed other left-hand and right-hand childs of those nodes. So, in summary, if the order of insertion and deletion is comparatively random, then we can achieve logarithmic performance. However, if we insert items that are close to or perfectly ordered, then the performance of the tree then degenerates to linear time, which is O of n. And finally, whilst we've covered the binary search tree in these videos, it's worth having a look further into other types of trees, such as the AVL tree, which is a self-balancing tree, as well as red and black trees as well. But for now, let's continue with the exercises and let's implement the insert, find, and delete algorithms. And so I'll get you started on that. Okay, so now that we've explored the thinking behind the insert process, the find process, searching our way through the tree, traversing it, as well as deleting nodes from the tree, let's have a go at implementing exercise 3 now, which we're given the pseudocode for the insert method. We now just have to translate that. Okay, so let's start with the signature. So we're in the public interface, and we're going to have a void return type, and then the method name is inserts, and then we take in this particular case, we're taking in a integer value that's called data, and that's what we want to add to the tree. Okay, so first things first, we're instructed to define a pointer, new node, and assign it a new node object passing data to the constructor. Okay, so let's break that down. We need to create a pointer. It's going to be a pointer to the node class. We're going to call it new node, and then assign it a new node object. Okay, and then we want to pass that integer value that we're getting in from the insert method, the parameter there, want to pass that directly to the constructor of node. Essentially, node is a wrapper class for this integer value. Okay, so we're just creating an object to wrap around that integer value. Okay, so that's that. And then next an if statement. And we're going to say if root is 0, i.e. if there is nothing in the tree already, we then want to make that item that we want to insert, new node, we want to make that the root. Okay, so we're going to assign new node to root within that if statement. Okay, that's straightforward enough. Now we get onto else, which is a big else statement. We've got a lot going on here. Here we're going to want to set up additional pointers to the current node that we're looking at. So this is kind of imagining that we can reuse this method for multiple points in the tree. So we're going to set up a pointer to current, and then we're going to set that current to root. And then we're also going to have a separate pointer to parent. Okay, so we can get access to left child and right child nodes of that particular node we're looking at. Okay. Next, we're going to set up a while loop, which repeats whilst true. Okay, and we're going to set parent to current. Okay, and next we want to then compare the data of the node that we want to insert with the data of the node that we're currently looking at within the tree. Okay, to work out if that data that we want to insert is less than the current data that we're looking at, we then want to pursue the left path of the tree. Okay, so here is where we'll say current is going to be current's left child. Okay, we're moving the position of current down one, basically, to allow us to then pursue that left path of the tree. Okay, and if there isn't then a left child, if there isn't a left child there, from that, if it's 0, basically, because remember we initialize all the left and right childs to 0 to start with. If that's null, we can then set the parent's left child to be that new node. Okay, so we then insert the node that we wanted to insert as the left child of the current node. Okay, where did I get to? New node. There. All right, and then I just want to break out of this infinite loop. Okay, and if, and then else. I imagine else is going to be the same, but for the right child. And yes it is. Yeah. So let's copy this and just change all the references to left child to right child. Okay, so exactly the same thing here. If the data is then greater than a particular nodes that we're looking at within the tree, we then pursue the right avenue and work out if there isn't a right child of that current node we're looking at, we make the item that we want to insert the right child, and then break out the loop. Okay, so. And let's just check we've finished off. Okay, so if and yeah, and loop and if and function. Yes, okay, we're good. So interestingly, this is actually an iterative solution, not a recursive solution, because you'll notice we're not actually calling the insert method within the insert method. Okay, so if you wanted an extension exercise, see if you can convert this iterative solution to a recursive solution. Okay, that would be a good thing to do, good thing to try out. But then when you've got this, when you've got either an iterative solution or a recursive solution set up, the next exercise, exercise 4, is where you get to test it out, because you're instructed to create an instance of the tree, insert 6 integers between 1 and 100, and then if they've been inserted in the correct positions within the tree, if your insert solution is correct, by invoking the display in order method, which remember prints left root and then right, that would then print the items within the tree in ascending order. So that could be how you can test whether your insert solution is correct or not. Okay, so let's give that a go.